Welcome to the 22nd lecture of the course Turbulence. So, in the last class we have talked about the turbulent kinetic energy equation for turbulent wake, okay, and we could approximate the value of advection term, production term, transport term and dissipation, and we plotted those terms across the wake width, and we discussed in details all these variation, and I mentioned that for further discussion of the same thing you need to go to Tenikens and Lumley and understand the better details of this kinetic energy budget of this turbulent wave flow. Okay. So, I am not going to talk about any more about this free shear turbulent flows which we started last couple of lectures back, and we could only talk about the wake flow in details, okay, and we do not have more times to discuss JED as well as mixing layer. So, I mean if you are interested, you please may proceed in the or you may proceed with the book Tenikens and Lumley. Okay. So, today we are going to start a new topic, and that is the wall bounded shear flows. Okay. So, we will start wall bounded shear flows. Okay. So, wall bounded shear flows, as compared to free shear flows, as the name suggests, these flows are bounded partly by walls. Okay. It may be in both the sides, for example, channel flow, or it may be in one side, for example, the flow over a plate or modular flows. Okay. So, this is what we are going to talk about, and mainly there are three wall bounded flows which are engineering which are very important from engineering point of view. For example, flow through channels, then flow through pipe, then flow over flat plate or boundary layers, for example, flow over aircraft to wing. These are the kind of wall bounded flows. Okay. So, these wall bounded flows are a bit different as compared to your free shear flows. Okay. So, because this for wall bounded flows, one important point here we need to keep it in mind is that the friction law or screen friction or friction at the wall, okay, which is very important because that gives some sort of screen friction drag. So, that is the reason that we have to find it out what is the screen friction at the wall for this sort of flows. Okay. So, the central issues for these wall bounded flows are mean velocity profile and your friction law. Okay. So, central issues or the main problem with these flows are your mean velocity profile, and friction law, okay, that is screen friction at the wall. Okay. So, this is what is the main issue with this sort of flows. Okay. Because observation shows, for example, if we consider the flow through a channel, and if you plot your velocity profile, that y by delta, delta is the half width of the channel. I will come back to, I will come to the a sketch of the channel flow, and suppose this is your u mean velocity divided by some bulk velocity u v, then the velocity profile, if you see, that it will look like something like this. Okay. And if you this is for one Reynolds number, then this is for another Reynolds number. So, this is lower Reynolds number, lower RE case, and this one high RE case. Okay. So, what it says actually this particular this type of flows depends on the Reynolds number. The velocity profile depends on the Reynolds number. Okay. So, higher the Reynolds number, the velocity profile will look like fuller profile, as you can see here. Okay. So, this is one of the issues, or how this velocity profile can be described. That is what is the one of the central issues of this particular type of flows. Okay. So, as I said, there are three types of flows, okay, mainly, and we will talk about so we will channel flow. Okay. This is flow through a rectangular duct, okay, and then pipe flow or circular pipe flow you can call, okay, and another is your boundary layer flow. Okay. Boundary layer flow or flows. Okay. So, these are the main three wall bounded flows often encountered in engineering applications. Okay. So, mainly we will talk about this channel flow in details as well as the boundary layer flow we will try to cover, and let us see how far we can go. If time permits, we will extend that discussion even in pipe flow, even for pipe flow cases. Okay. So, all right. So, first we are going to talk about channel flow. Okay. So, channel flow, and let us consider a channel. Okay. So, let me draw the sketch. So, this is the height of the channel, which is 2 delta, okay, and width let us consider it is b, okay, and length, this is what is our length, that is L. Okay. So, and our coordinate system is fixed at the center line at the lower wall, and y positive in this direction, x is in the direction of the flow, and z is the span wise direction. Okay. So, here there are two flow velocities, one is called center line velocity. So, center line velocity, let us say u c. So, u c is center line velocity, and we will consider another velocity which is called bulk velocity u b. So, this is known as bulk velocity, okay, which is defined as u b equals to 1 by delta 0 to delta u mean velocity dy. So, this is the definition of bulk velocity. So, and 2 delta is the height, 2 delta is the height of the channel, okay, and b is the width of the channel, and L is the length. Okay. All right, and we can define Reynolds number based on, so RE based on the bulk velocity, and total channel height is denoted by RE for this particular case. So we will consider UB twice delta. Okay, this is our the height of the channel divided by nu. Okay, and another Reynolds number based on the center line velocity of the channel, which we will call REC, and this is UC delta by nu, and this is based on the half height of the channel. Okay. So these are the two Reynolds number. Okay. So these flows, we will talk about only developed channel flows. So initially, when there will be a flow through this channel, there will be a developing region of the flow. Okay. For example, if let me just draw it here, let us say if I draw the cross section of the channel. Okay. This is what is your cross section. So the moment the flow will be inside, so there will be a boundary layer which will develop and meet somewhere downstream. Okay. So there is a flow through this, let us say U, and then this is what is the boundary layer. So if you draw a velocity profile somewhere here, it is going to look like this. Okay, like this. So velocity profile similarly somewhere here, it will look like this, then like this. Okay. So slowly the velocity profile is developing. So here if you see, it is a constant velocity. Okay. There is a slight proportional issue here. So something like that it should be, as it is going downstream, the velocity should be at the center line velocity within this potential core. This is known as potential core or potential regime. Okay, this is the viscous regime, this particular part within this boundary layer, and this particular part outside of the boundary layer, the flow can be considered as potential flow. So the velocity should increase. So the profile should look like something like this. Okay. So finally we will get a developed region where the velocity profile for laminar flow, it will appear as parabolic. Okay. I expect that you know all this. Okay. For a laminar case, this profile will be parabolic, but if it is turbulent case, the profile will be fuller, and it will look like this. For turbulent velocity profile, it will look like this. Okay. So this is what is your laminar profile, the white line, and this yellow line is sort of your turbulent velocity profile, and this profile is take this particular shape, that is all enhanced mixing. Okay. Due to enhanced mixing in the flow, this profile will be fuller. Enhanced mixing means enhanced turbulence diffusion. The profile will be something like this in a channel flow. Okay. And of course these are the channel wall. Okay. So we are going to talk about only the fully developed portion of the channel flow here. Okay. So for this fully developed region, the statistics are independent of streamwise direction x. Okay. So that is one point we have to keep it in mind. So in that particular case, then we can consider this del u del x equals to 0. Okay, because the streamlines are going to be parallel to the surface of the channel, right. So this is the case for fully developed channel flow. Okay. Okay. So for fully developed channel flow, the statistics with respect to the streamwise direction is going to be 0. Okay. We should keep it in mind. So this we are considering because this particular quantity is very useful, will be very useful for us. Okay. So in this particular case, that for this along with this, another point which we need to mention here, here with what we are going to talk about, the channel flow, this particular quantity is much less than 1, and V by delta by V is also much less than 1. Okay. So, we are considering a flow for which the half height of the channel is much less than the length of the channel, and the half height of the channel is much less than the width of the channel. Okay. So, that is one thing, and that velocity for through the channel will be predominantly in the streamwise direction or in the x1 direction. Okay. So, anyway we can that velocity vector we can say as u v w, which in terms of initial notation 1, u2 1, u2 3, and corresponding fluctuating quantities we will consider as u v w, which are fluctuating quantities, which in terms of your initial notation will be something like this. Okay. That these things I believe you know, but for this particular channel flow case the w will be 0. Okay. So, the span-wise component of the mean velocity will be 0 in this particular case, as well as we will see from the continuity equation. For example, if we consider the continuity equation, then it is going to be del u del x, okay, plus del v del y, mean continuity equation, which equals to 0. Since del u del x is equal to 0 for fully developed channel flow, this implies that del v del y is equal to 0. Okay. Del v del y is equal to 0 means v, that if you integrate this implies if you integrate that v can be a some constant of x. Okay. Now, where that c of x means some constant of x, but at y is equal to 0, at y is equal to 0 at any x location, the v velocity is 0. That means, at any x location this constant is going to be 0 at the wall. Okay. If it is going to be 0 at the wall, then it has to be 0 all through. Okay. It has to be 0 all through, because v does not change with y. Okay. So, if it is 0 at the wall, v has to be 0 everywhere. That means, for this particular case your v velocity is also equals to 0, mean velocity v is also 0. Okay. So, we should keep this in mind. Okay. So, now we will consider the momentum equations, okay, to find out the solution for this particular flow. And if you can remember that our momentum equation u j del u I del x j, that mean momentum equation. Okay. So, this equals to so this can be written as del u I u j bar del x j equals to what, minus 1 by rho del p del x psi plus nu del 2 capital U I del x j del x j, right. This is what is our averaged Navier-Stokes equation. Okay. Here that P is also average quantity. Okay. So, from this equation, then since W is 0, so we will have two momentum equation, okay, which can be found from this for I is equal to 1 and I is equal to 2. So, if you consider the momentum equation corresponding to I is equal to 2, that is nothing but our y momentum equation. Okay. So, the y momentum equation from this particular equation, okay, this equation let us call this equation as 1. So, from this equation 1 we can write the y momentum equation. Okay. So, let us do that. We get the following. y momentum equation, right, for I is equal to 2, right. So, for I is equal to 2, if I write that equation in terms of u v and x y, then we will be able to find this equation, okay, from equation 1. Okay. So, this is what is the equation for, sorry, I have written that x momentum equation. So, let me write the x momentum equation, and so let us say this equation is equation number 2, and we can write similarly. So, similarly we can write the y momentum equation, okay. That is going to be u del v del x plus v del v del y plus this is v square bar del y plus del u v bar del x equals to minus 1 by rho del p del y plus nu del 2 v del x 2 plus del 2 v del y 2. Okay. Let us say this is equation 3. Okay. So, okay. So, these are the two equations. First, we will simplify equation 3. Okay. Let us see what are the terms which are going to survive in equation 3 with the assumption that the flow is fully developed. If the flow is fully developed, then del u del x is equal to 0, which says del v del y is equal to 0, which again implies that v is equal to 0 everywhere. Okay. So, if this is the condition, then this is going to be 0, this is going to be 0. Okay. What about this? What about this? Statistics will vary with respect to y, because we have only considered statistically independent in the main streamwise direction. Okay. So, that means this statistics is going to be 0 along the x direction. Okay. That is what we have considered at the beginning, keep it in mind. And what about these two quantity? These are also going to be 0, right. These are also going to be 0. That means from this equation, what do we get? We get that del, if v square is not a function of x, okay, if this statistics is not a function of x, we can put this as total derivative, right. So, this plus you see 1 by rho dp dy is equals to 0, right. So, this is what we get from this simplified y momentum equation. Now, this will integrate, if we integrate, then in the right hand side what we will get? We will get a constant which can be a function of x, but that cannot be a function of y, because if we integrate with respect to y, the right hand side we can get a constant, and that can be a function of that can be a function of x. Okay. So, if you do that, let me do it somewhere here. Integrating, we get, okay, what do we get? Integrating with respect to y, keep it in mind. So, v square, right, plus p, capital P by rho equals to some constant which can be a function of x. Okay. So, let us say it is C1, which can be a constant which can be a function of x, right. Now, let us consider okay, this is the equation, and let us consider the value of this constant at y is equal to 0, okay. And at y is equal to 0, let us consider the pressure to be Pw, means pressure at the wall. So, at y is equal to 0, let us designate that P, okay, is equal to Pw, okay. If this is the case, then you see at y is equal to 0, then this particular quantity is 0 and this is going to be Pw then, okay. So, at y is equal to 0, so at y is equal to 0, this above equation will be then Pw by rho, okay, equals to your C1 of x, okay. So, still it says that this Pw then can be a function of x, okay. So, Pw can vary with respect to x, that means then this equation, okay. So, this particular equation, okay, let us say this equation is your equation 4. So, hence your equation 4 will be as follows, okay. So, what it is going to be? It is going to be your v square bar plus p by rho equals to that constant is Pw, which can be a function of x as per this by rho, okay. Note that p is a function of both x and y, okay. That is why we have kept this particular term in both the x and y momentum equation, because we have kept that term del p del x as well as del p del y, okay. So, if this is the case, this is what we get, and let us say this equation is equation 5, okay. Now, what do we do? From this equation we can find out the streamwise pressure gradient. How? We just differentiate this equation with respect to x, okay. If we differentiate this equation with with respect to x, so what do we get? So, differentiating this equation, so let me do it here, okay. Equation 5 with respect to x, we get what? We get one very important relation, that is dp dx, okay, equals to, sorry, it should be partial, because p is a function, left hand side p is a function of both x and y. The left hand side p should be a function of, should be partial. The right hand side we can write Pw dx, okay. So, let us say this is our equation 6. So, equation 6 shows that the dp dx is equal to dpw dx, okay. So, what it says? It also says another important thing, the dp dx does not vary with y. So, this is also showing something very interesting, that dp dx, because the right hand side is the sole function of x, okay. So, the dp dx essentially does not vary with y, okay. So, that is what it, in the pressure gradient, streamwise pressure gradient does not depend on y, that is what it says. All right. Now, what we can do? We can consider now the x momentum equation here, okay. So, now we can simplify this x momentum equation, and let us do it what we get if we do this. So, for fully developed channel flow, our this particular quantity is 0, V is 0, this is also 0. Statistics does not depend on the x direction, this should be 0, this should not be 0. We expect that Reynolds state should vary across the width of the channel, sorry, across the height of the channel, okay, and this first part of this is equal to 0. So, we will be left with 3 terms from the equation 2. So, from equation 2, what do we get, or we can just write del y equals to minus 1 by rho x plus nu del 2 u del y 2. Okay. So, now another step, see what we got, this particular quantity u, we said that del u del x is 0, u is not a function of x then, u is only a function of y for the case of fully developed channel flow. So, that means this can be total derivative. What about this? What about this? Reynolds stress, statistics is not going to depend on x direction for fully developed channel flow. That means this also can be total derivative, right. So, we can write this equation as d u v bar dy equals to minus 1 by rho del x plus nu d2 u dy 2. Okay. That is what we can write. And next line, from next line, so what we can do, this is viscous shear stress or related to with viscous shear stress term, this is Reynolds shear stress term. So, what we can do, we can take these two terms in the left hand side and rearrange this equation, then what we can write, minus mu by rho, okay, d2 u dy 2, this quantity d u v dy equals to minus 1 by rho del p del x. Okay. Let us again rearrange, let us do it here. So, let me just clean it. I can write this equation as, I can multiply by rho in both the side and multiply by minus 1 as well. Then what I can get, I can write this first term as this plus or let it be there minus rho u v, okay, dy equals to what I get, del p del x, right. This is what I get, or I can write d dy mu minus rho u v bar equals to del p del x, right. So, you see what is this left hand side term? This particular term includes both the viscous shear stress and Reynolds shear stress. So, this is actually total shear stress term. Okay. So, let us call this left hand side term, let us call tau v t, okay, dy equals to del p del x, where tau v t total shear stress viscous plus turbulent, okay. That means mu du dy minus rho u v bar, okay. That is what it is, right. Now, see dp dx, dp dx or sorry del p del x, we have got del p del x is equal to this. So, from equation 6 we can put the value of del p del x in this particular equation. Okay. So, or d to Vt equals to dy is equal to del p del x, we got it p w, which is a function of x and dx. Okay. Very interesting. Very interesting thing. You see u, which depends only on y. This statistics does not depend on x. So, this entire quantity is just a function of y only. So, that means tau Vt, so which is summation of viscous plus Reynolds stresses, is function of y only. So, this left hand side can be a function of only y, whereas in the right hand side it is just a function of x. So, what it says, if we integrate, that means both the terms should be constant, that is what it says. Okay. So, that means if we integrate the tau Vt, so we can say integrating we get integrating what we will get tau Vt equals to dpw dx y plus some constant c. Okay. That is what we will get, right. Now, this constant c can be found out with some proper boundary condition. Okay. See, at y is equal to 0, what is the value of tau Vt? That is what we have to find it out. Okay. So, c is a constant here. Okay. So, to fix this constant, we have to use the boundary condition. At y is equal to 0, we have to find out what is the value of tau Vt. What is the tau Vt? Tau Vt is this. Okay. So, what does it say? At y is equal to 0, Reynolds stress is going to be 0 from the, because u is 0, v is also 0 at the wall. So, this part is definitely 0, and this part at y is equal to 0, this expression then becomes tau w, okay, wall shear stress then. Okay. So, at y is equal to 0, tau Vt becomes tau w, that means c is equal to your tau w. So, your c becomes tau w, right. Let me use this space. From this equation, what do we get? That tau Vt equals to then dpw dx y plus, what do we get? Tau w, because the constant c is found to be tau w, that is what we get, right. Now, we will do one thing, this tau Vt, okay, let me draw the tau Vt, this is what is our channel. Okay, let me put the cross section, sorry. So, this is what is the center line, this is the wall of the channel. Okay. Let us say it is far downstream from the entrance of the channel, so that we are in the fully developed region and turbulent flow. And by the way, I have forgotten to mention one more point, that since we are talking about turbulent channel flow, here the Reynolds number based on the bulk velocity and the total height of the channel should be greater than 1800, although that means we are talking about Re of course greater than 1800. Okay. because for that only a channel flow can be turbulent, okay, although the transitional effect can be noticed till 3000 anyway. So, this point I just forgotten, I am just mentioning that we are considering the channel flow which is greater than this particular Reynolds number, and this particular Reynolds number is based on the bulk velocity as well as the the channel height. Anyway, now what is the point we would like to mention? Physically, can we say whether tau Vt is going to be a symmetric function about the central line or it is going to be asymmetric? Okay, it is going to be asymmetric. Why? Because observation shows, as I already told you, observation shows that velocity profile is something like this in a channel flow. Okay. If the velocity profile is something like this, if you consider this particular portion, and here we have considered y 0 at this wall and x in this direction. Then in this particular part, if you consider your velocity gradient, which is always positive, because for any delta y, delta u is going to be positive. But in the other side of that, what is going to happen? The other half, it is opposite. For any delta y, your delta u is negative. So, that means at the wall, if tau w which is equal to mu into du dy at y is equal to 0 is positive, okay, is positive at this wall, and this quantity is going to be negative at this. So, if it is tau w at this wall, then in the other wall it should be minus tau w, okay, because due to this velocity profile, okay, because within this du dy should be positive, after that it should be negative. That means this du dy from this velocity profile also it is very clear that it is 0 at the central line. Okay. So, that means the viscous stress at the central line of the channel flow is 0, and in the lower half of the channel it is going to be viscous stress is going to be positive, in the upper half it is going to be negative due to the velocity gradient. Okay. Velocity gradient in the upper half is going to be negative. Why? For any delta y in the negative portion, the delta u is going to be negative. Okay. So, delta u divided by delta y, which is nothing but your du dy, is going to be negative for this part. So, that means the viscous stress is asymmetric about this. So, viscous stress, you will see the viscous stress, if you plot, it is something asymmetric, maximum value is somewhere here, then it will be something like that. Okay. So, this is what your viscous stress, it may not be linear, but anyway something like that you will get it. Okay. So, this is asymmetric, viscous stress is asymmetric about this central line, which is positive lower half, negative upper half. What about the minus rho u v, this particular quantity? So, because we are talking about the tau Vt, that viscous stress du dy minus rho uv. Okay. It includes both. We are trying to find out whether this is going to be symmetric or asymmetric about the center line of the channel, right. So, you see this particular part, what is going to happen in this particular portion? See, if I blow it up that particular portion, it will look like something like this. So, a fluid parcel, when it is going from this to this location, it is trying to transport which one? Lower momentum from this location to this location. As a result, at this particular location, it is trying to reduce the mean velocity. As a result, the fluctuating quantity u fluctuation is going to be negative, but since it is moving in the upper direction, v fluctuation is positive. So, the multiplication of u v is going to be negative. That means minus of rho u v is going to be positive for the lower half. So, in fact your Reynolds stress also, Reynolds stress profile, if you draw somewhere here, so Reynolds stress also, it is going to be 0 at the wall, then somewhere it is going to be slowly positive, then it is going to be negative. Okay. Why negative in this other side? Other side, why it is negative? other side it is going to be negative. That is all because of the fact you see this particular portion. Consider this particular portion. This is what is your wall. This is what is your velocity profile. Okay? And y is positive in this direction, x is positive in this direction. So, your fluid particle is going from here to here. What it is trying? What it is trying to? It is trying to increase the momentum at this location, because it is the fluid particle is going from the high momentum zone to low momentum zone. So, as a result, the instantaneous the velocity is going to be more there. Okay? As instantaneous the velocity will be more there as compared to the mean velocity. As a result, your u fluctuation will be positive, and since the particle is going in this direction, in the positive y direction itself, that rho uv is going to be positive, but one minus sign is already sitting, so it has to be negative. Okay? So, this is we are talking about 0 location. So, that means you see both viscous as well as your Reynolds stress, both are asymmetric about the central line, and in the upper upper portion of the central line both the stresses are negative, in the lower portion of the central line both the stresses are positive. As a result, the tau Vt is essentially, this tau Vt, this quantity is essentially asymmetric about the central line. Okay? Since it is asymmetric about the central line, the total stress has to be 0 at the central line. Okay? That means, at y is equal to delta from this equation. So, if you put y is equal to delta, your tau Vt at y is equal to delta is 0. Hence, at y is equal to delta, tau Vt from this argument is equal to 0. From this equation, then what do you get? At y is equal to delta, as at y is equal to delta 0, we get from the above equation. What do we get? You see dPw, keep it in mind, dPw is a function of x, okay, or Pw is a function of x, delta plus tau w, this is going to be 0. Okay. So, what it says dPw dx equals to minus tau w by delta. Okay. And let us say this equation 7, let us call this equation to be 7. Okay. So, now if this is the case, then if this is the case, then this equation can be, in this equation, then you can replace this particular term with this minus tau w by delta in this particular equation. If we do that, then what do we get? We can write, hence your tau Vt equals to, replacing the value of p tau w by tau minus tau w by delta y plus tau w, or tau Vt equals to tau w 1 minus y by delta. Okay. Let us say this is equation 8. Okay. This is very important equation. Okay. So, you see tau Vt, total shear stress, varies as this. Okay. So, total shear stress, how it varies. Now, let us draw it. Okay. Of course, from this particular equation 8, one can see it is just linear function. It is a basically for a given tau w, it is linear in y, right. So, it is just a straight line till y by delta is equal to 1 at which the tau Vt should be 0 as per this equation. So, that is this axis, if it is y by delta, this is going to be 1, where the value of this tau Vt by W, or you can write this is nothing but your tau Vt divided by tau W equals to 1 minus y by delta, right. So, that means this is what is your your this quantity. So, this line is nothing but this, okay. So, or you can say this is tau Vt divided by tau W, right, this axis. Now, you see interesting point here. Let us look at the okay, I have just removed it. So, let me write this this particular equation. Okay, equation 8 can also be written as equation 8. If you see the left hand side of the equation 8, what is that particular term? D du dy minus rho uv bar, that is what is your left hand side of this equation, equals to tau w 1 minus y by delta, right. So, at y is equal to 0, this quantity is 0. That means, at this location, the stress is completely given by, at y is equal to 0 location, this is 0, y is equal to 0. At y is equal to 0 location, the stress is completely viscous stress, wall shear stress. Okay. So, as you are increasing y, then your Reynolds stress is going to increase, then this quantity is going to decrease. Okay. So, that means your your wall shear stress will, let me use different color. So, wall shear stress, if this is the wall shear stress which is maximum at the wall, is going to decrease as you are increasing the y distance, okay, and it is going to be negligible little bit away from the wall. Whereas, if you consider your Reynolds shear stress, which is this, which is slowly picking up, okay, and it is going to be something like this. Okay. So, this is your actually minus rho u v quantity, and this particular one is your mu du dy quantity. Okay. So, this is Reynolds stress, sorry, this is Reynolds stress and this is shear stress, summation of these two is this line. Okay. So, that means, as you are away from the wall going towards the central line where the total shear stress is 0, okay, as you are away from the wall, your wall shear stress is reducing, whereas your close to the wall, that Reynolds shear stress is increasing and taking a peak somewhere near the wall, then again it is decreasing in the outer side, right. So, that is what this particular relation says. Okay. So, here this particular derivation shows that the channel flow is completely described by this particular quantities, for example, rho, nu, delta, as well as the Pw or gradient of Pw at the wall. Okay. But one thing, this particular shear stress relation, this shear stress relation is actually, it is actually independent of rho, nu, these quantities. Okay. These are independent. So, now important point here, that total shear stress is given by this particular expression. Okay. So, So, now with this, so this is the kind of your total shear stress, the variation inside the turbulent channel flow. Now, we are going to talk about the velocity profile in a turbulent channel flow, how the velocity profile is going to change. Okay. So, one thing needs to be pointed out here, as I mentioned, that the channel flow is going to be completely specified by. Before I proceed, let me just give you another brief overview. See, in the case of free shear flows, this particular part, the viscous part, was negligible, okay? Whereas only this quantity is important in free shear flows, this quantity is negligible for free shear flows, okay? Because free shear flow is not bounded by walls, okay? So, that is one very important observation comparing these two flows, okay? Now, velocity profile as I talking about, okay? So, velocity profile, that is what we are going to talk about. As I mentioned, a channel flow is going to be completely specified rho, nu, delta and dp w dx, or equivalently by rho, this is nu, okay, rho nu delta and u tau, okay. So, here before we proceed, some of the discussion is needed. So, what is u tau? Okay. U tau is known as friction velocity. So, near the wall, we need to figure it out the right length and velocity scale, because as you see, near wall dynamics is governed by this particular equation shows that very close to the wall, the total shear stress is mainly dominated by viscous shear stress, okay, very close to the wall. That means that right velocity and length scale should be different near the wall. So, we need to figure it out. So, one velocity scale which is designated as u tau is known as friction velocity, okay, is defined as tau w by rho, okay. This is what is our friction velocity, okay. Tau w by rho. What is tau w? You see, this quantity we can write minus tau w by delta into minus delta by rho, okay. Or you see, what is this? Tau w minus tau w by delta, what is this quantity? Minus delta by rho dp w by dx, okay. That is what we said, that a channel flow is going to be completely specified by these variables or by these variables where that dp w dx is usually related with the friction velocity u tau. The friction velocity is the velocity scale appropriate for close to the wall, okay. Similarly, the appropriate length scale close to the wall is known as viscous length scale. Okay. So, viscous length scale is defined by, okay, delta V is nothing but your nu by u tau. Okay. So, this is what is your viscous length scale. Okay. So, this viscous length scale and viscous velocity scale, which are actually important close to the wall. Okay. Anyway, with this, and another point here we need to mention that sometime this one parameter, let me use the other space, not parameter, variable y plus is very often used, okay, in the literature, and you have to also know about it, what is y plus. So, y plus is important close to the wall, and it is a non dimensional distance from the wall which is relevant near to the wall. So, y plus is nothing but y divided by delta V. Okay. When y is normalized by the viscous length scale close to the wall, we call this quantity as y plus. Okay. And so, delta V is y, delta V is, as we said, nu by u tau, right, nu by u tau. So, this is y u tau by nu. Okay. So, that means y plus is equal to, important, keep it in mind all the time, y plus is equal to y u tau by nu. Okay. This is one important non dimensional quantity, okay, we should keep it in mind. Okay. Another quantity, that is R e tau, that Reynolds number based on the u tau. So, this is defined as u tau delta by nu. Okay. This is what is your turbulent Reynolds number, it is mentioned as turbulent Reynolds number. Okay. So, it is not mentioned, called as turbulent Reynolds number. Okay. This is turbulent Reynolds number, right, and you see, since your delta V is equal to nu by u tau, what it says, this Reynolds number based on the u tau delta V by nu is 1. Okay. Keep it in mind. Anyway, so with this, now with this introduction, now let us consider a channel flow. Since it can be completely specified by these variables, then its velocity dimensionally should depend on these variables. That is the takeaway message from this. That means your velocity, mean velocity, dimensionally can be written as f naught, so is a function of y by delta R e tau, okay, where f naught is a universal function. Okay. F naught okay. So, this is what we can get, that u should depend on two parameter. One is y by delta, which is a non dimensional parameter. Once again, R e tau is also non dimensional parameter. Okay. But instead of mean velocity in the channel flow, very often the gradient of mean velocity is very important, because the gradient, for example, the production depends on gradient of mean velocity. Similarly, your shear stress close to the wall depends on the gradient of the mean velocity. So, instead of writing the dependent variable in terms of independent variable in this particular fashion, we can write actually in based on the dimensional ground itself without any assumption, based on the dimensional ground and without any assumption, we can then instead of u, we can then mention that this phi y by delta y by delta v. Okay. So, instead of writing the mean velocity as a function of some non-dimensional parameters, we can write that gradient of the mean velocity itself in this fashion, and that also based on completely non-dimensional ground. Okay. So, this is the way without any assumption we can write this particular equation. Okay. So, this is one interesting point to note. Okay. So, now what we can do here, you see we can non-dimensionalize both the side, or this equation we can write this equation, or this equation you see there should be u tau here. Okay. One u tau should be here. Okay. So, this equation then can be written as d u plus d y plus equals to 1 by y plus phi of y by delta, and 1 by delta v is nothing but of y plus, or let us write delta v at this point of time. That means, see, this is what is your this equation, okay, non-dimensional equation which you can find. Okay. So, this particular equation, you see, Prandtl argued, okay, that this equation or the mean velocity gradient becomes independent of this particular quantity as we go away from the far away from the wall. Okay. So, far away from the wall, this particular functional form solely depends on y by delta v. It becomes independent of y by delta. Okay. That is what was the postulation of Prandtl. Okay. So, as per Professor Prandtl postulation, this phi 1 is a function of y by delta v only in the limit of y by delta tends to 0, this phi y by delta v. Okay. So, in the limit of y by delta tends to 0, this phi function becomes just a function of y by delta v. Okay. So, from this then we can write, or we can write du plus dy plus, sorry, one point I have forgotten to mention here, that u plus is nothing but your u by u tau. Okay. That is what is known as u plus. Okay. So, this equals 1 by y plus phi 1 of y plus. Okay. Or we can write du plus, or we can write from this integrating we get after integration what we get, u plus is equal to f w of y plus, where f w of y plus is nothing but of 0 to y plus 1 by y dash phi 1 of y dash dy dash. Okay. This is what we get. Now, you see from the from the boundary condition at y is equal to 0, your u plus is also going to be 0. Okay? U plus is going to be 0. Hence, that f w of 0 is equal to 0. Okay? This is one condition we get. Okay? So, another condition, what we can get, if we take the derivative of this. So, the derivative of this is nothing but y plus equals to du plus dy plus. Okay? And this is equals to your basically nu u tau, this is u tau square, then this is going to be du dy. Okay. So, u tau square, that means you see that mu by rho u tau square du dy, right, and this is you see, then f w prime at y is equal to 0, f w prime at y is equal to 0 is equal to this quantity, that means mu by rho u tau square du dy, this is at y is equal to 0, okay, which is nothing but 1. Okay. So, that means this particular quantity very close to the wall can be expanded using Taylor series, and we can use these two value to find one very important result very close to the wall, y is equal to u plus. Okay. So, this particular relation which is very close to the wall becomes u plus is equal to y plus, is known as law of the wall. Okay. So, we will come back to these particular discussions once again in the next class, since today time is over, we will not be able to continue the discussion. Okay. Till this point, okay, let us stop, and thank you very much.